on. So right before I start, just take a look and see if it isn't shifted. Okay, thank you. Make sure it's recording. All right. Good afternoon, everyone. Thank you. Thank you. Okay, first things first, you have a homework assignment due this week, Friday. I'm going to have a very short quiz. There's not much to think about it. It's just a feedback quiz that will be due on Thursday this week. Focus on the homework. Okay? The homework is due on Friday. You're going to have one more homework assignment for the next week, and then we come to our second exam. And as I have mentioned, as you're seeing in class, the material for the second exam is going to be much more difficult. Okay, this is not by design, this is how the system is set up. Okay, but with that said, we will get to understanding the concepts so that we can do a good job in the second exam as well. All right, I'm going to start second order step response. Okay, thank you. So we've done free response of first order systems, we've done step response, ramp response, impulse response of first order systems, we've done delayed time response of first order systems, we've done free response of second order systems. On Carmen, I have uploaded an example problem on second order time delayed systems. Okay, the approach is the same, the idea is the same as first order, nothing different from it, you just take Laplace transforms. This one is the response of a second order system to a step input, has a special meaning because one can perform, hypothetically, experiments on physical bodies which would give us a step response. And using that, one could understand how the system evolves as a function of time. Okay? So this has some special meaning for us. I'm going to start with the spring mass damper equation. This is just some generic second order equation. Okay? So mx double dot cx dot kx. This is a generic second order system where m, c and k are at this moment the mass, the damping constant and the stiffness, but if you do electrical systems they could be different. The meaning is the same, okay? And then this is equal to f naught u of t. This is a step input of magnitude f naught. And And we're going to consider only the forced response of the system because we already know what the free response is. So for us, x of 0 is 0, x dot of 0 is 0. So we are studying the forced response. We already have studied the free response, so we don't need to dwell on that again. What do? We first write it in the standard form, right, by dividing through by the mass. So these are all fundamental steps. We do this for every second order system. So I divide through by the mass. F naught by m times u of t. Okay? And then we say that the C by m can be replaced by the quantity 2 zeta omega n. Where zeta is C by 2m omega n. Omega n square is the square of the natural frequency of the system. Zeta is the damping ratio. It's a dimensionless parameter that governs how the system response changes. And this equation can now be cast in the standard form. Okay, so I have x double dot 2 zeta omega n x dot omega n square x is f naught by m u of t, and initial conditions are switched off. This is the system we are going to study. Okay? And once again, what is the purpose of Laplace transforms? For us, of course, Laplace transform has great purpose. Our purpose is very narrow. We use Laplace transforms to solve differential equations. That's all. The buck stops there. Okay? So I'm going to use the Laplace transform, take Laplace transform on both sides, and we will bring it to the form that is ripe for some amount of thought-provoking discussions. So let me take Laplace transform on both sides. I have the following. Because I have no initial conditions, because I'm studying only the forced response, this is what I end up on the right hand side if I take the Laplace transform. And on the right hand side, I'm taking the Laplace transform of the step function. The unit step function has a Laplace response of 1 by s. The magnitude is now modified by this factor of f naught by m. Okay? The m comes because I'm dividing through by the mass to bring it to the standard form. Okay? So this is the standard form. Or quite simply put, x of s can be written in the following manner. Is f naught by m by s times please notice if you have a denominator term of s on the right hand side, that belongs to the whole denominator itself. Okay? So this term gets attached to the characteristic polynomial, right? This is the characteristic polynomial. We take the roots of the characteristic polynomial. If you use MATLAB, you would first want to find the roots of this and then break it up into coefficients and then feed that into MATLAB and then obtain the results. So we do that by hand for this problem. Okay? So the roots, same as before. Minus zeta omega n. These are the roots. And as you know, there are three cases. When zeta is positive, I could have either zeta greater than 1, zeta equal to 1, or zeta less than 1, right? The more interesting of these three cases is the case where zeta is less than 1, because it shows oscillatory behavior. And that's what most systems also exhibit that are quite useful, or you can make systems exhibit such behavior. Okay, so I'm going to study the behavior for zeta less than 1, so choose. Zeta is positive, or at the worst case equal to 0, and less than 1. We expect underdamped behavior, which means we accept sines and cosines, or expect sines and cosines. And so the roots of the characteristic polynomial, we have written this before. Plus j times omega d minus j times omega d. This is all old news. We've done this for free response. Okay? So the characteristic polynomial can be written in terms of the roots, and so we have the following. S square 2 zeta omega n s is now s plus zeta omega n whole square plus omega d whole square, and this is also something that we had written in the past when I did free response for underdamped systems. Okay, so please take a look at it. I believe it's lecture 22 and 23. We were able to write the roots in this following form. And with that said, I go back to my x of s and I say, okay, x of s is f naught by m, all of this good stuff in the denominator. Do not forget the factor of s, because that is where the step response comes into play. And then we split this, because we expect sinusoidal solutions, we split this into three pieces. First piece will handle the s term, so this is c1 by s. Then the second piece is going to give us, upon partial fraction decomposition, sines and cosines, c2s plus c3 by s plus zeta omega n whole square omega d whole square. All right, I hope there are no surprises so far. Okay, there will be some later on. My aim is to calculate C1, C2 and C3 very quickly. Let's do this, okay, and then I'll hand wave on the solutions. So, in order to calculate C1, C2, C3, you take a common denominator, you multiply throughout. This is doing things by hand, the less glorified manner. Okay, MATLAB can do this in a fraction of a second, but you need to know how to do these by hand. All right. So f naught by m, this is c1 multiplied by the quadratic polynomial, c1 s square, and this is 2 zeta omega n s omega n square, c2s plus c3 multiplied by s. I'm taking common denominators, trying to find out C1, C2 and C3 in terms of the parameters of the system, which will give us a very generic solution which can be adapted to any kind of a system that undergoes step response. Okay, which is why we are not putting numbers in yet. I can calculate C1, C2 and C3 by using the coefficients of s square, s and s to the power 0 on both sides. Nothing on the right hand side. Left hand side I have C1 and C2. Coefficient of s to the power 1 on the left hand side, there is nothing on the left hand side, so that's 0. On the right hand side I have C1 times 2 zeta omega ns times S. So that's 2. And I have C3 times S. Okay, so plus C3. I do the same thing for s to the power 0. F naught by m. And I have C1 times omega n square. Omega n square is k by m. So I have k by m. C1 is equal to F naught by m. Which tells me C1 is F naught by k. This is an important result. C2 is negative of C1 minus F naught by k. Substitute for C3, calculate C3 minus 2 zeta omega n F naught by k. Okay, these are the three things. And I will of course not continue all along. If I now write my x of s, I have the following. Is F naught by k by s, right? C1 divided by s. Then I have C2s plus C3. I'm going to write C2 separately. Okay, so that's minus F naught by k times s plus zeta omega n whole square omega d square. So this is C2 times s divided by the denominator term. And the same thing for C3 minus 2 zeta omega n F naught by k and 1 s plus zeta omega n square omega d square. People in the back, can you see my writing? And you know the trick that we typically employ here. The inverse of the first term should give me a step function. The inverse of the second term after doing some manipulation should give me a cosine. The inverse of the third term should give me a sine. Okay? So the manipulation that we do is plus zeta omega n minus zeta omega n. I'm not going to go through with it. I'm going to just get the inverse now. I have it in my lecture notes. So x of t is the following. Okay? So x of t F naught by k, if you look at it, F naught by k is a common factor, so I'm going to take it out completely. This is the solution. Multiplied by 1. I'm going to reduce the volume a little bit. Can everybody still hear me? Without the echo? Alright, and then I have, because this is a frequency shifted term, right? This zeta omega n is a frequency shift, I'm going to have an exponential term there. Okay? So e to the power minus zeta omega nt. Inverse of the middle term is going to give me cosine omega dt. Plus, after some manipulations which I'm not going to do here, we are going to spend our time doing better things. Zeta by 1 minus zeta square this is the solution. We typically do not want to write it as cosine something plus sine times something. We want to write it as a phase shifted sine or a phase shifted cosine wave, right? So we do further manipulations and the same thing. can be written in the following manner. Okay, so x of t is f naught by k, nothing happens there. That 1 is nothing but the step function, and so this is essentially for t greater than or equal to 0. I'm avoiding writing the step function by saying, okay, this is only for positive time. Okay? So f naught by k, the 1 remains, can't do much without that 1. E to the power minus eta omega nt, that's the envelope of the decaying curve, so you cannot get rid of that creature. I'm going to put a term called c, it's a constant, cosine omega dt minus psi, where c is 1 by square root 1 minus zeta square, and tan psi is zeta by square root 1 minus zeta square. With your silent permission, I'm going to erase this portion of the book. Okay? And then we'll use the top panel after that. What are these two things called? They're called the step response of a second order system. They are the same things. They're not any different. I just manipulated the first one to get the second one. I manipulated A to get B. Okay, so these are the step response. Your book gives you a third way of writing the same thing. I typically would not be using it, but I want to present it to you to say that we are all on the same page. We are doing the same thing that your book is also espousing. Okay? So from the book, if you have it, this is the third way of writing it. Okay? So x of t is f naught by k, 1 plus c e to the power zeta omega nt sine omega dt plus some, I think your book calls it phi, so I will use the same Greek letter as your book. This is chi, so phi. What is phi here? What is c here? This is the same thing. C is the same as what you have. Okay, and then phi is 3 pi by 2 minus psi. It's not necessary, you can use any one of these forms. I'm going to stick with form B, it's the least complicated of the lot. But this is what your book does, so I want to present it to you. And this is, I believe, tan inverse square root of that plus pi. Okay, so this is your book. Form B is what I'm going to use. They are all the same. There's no difference between the two. You just manipulate one to get the other. The great news is if I have a combination of cosines and sines, I can write it as a phase shifted wave, a waveform. Okay? Alright. I want to see if there are any questions so far. A lot of Greek and Latin. So we will try to make sense of it. Why are we doing this? Quick recap, second order system, step input. We are looking at the forced response. No initial conditions. Go through the same procedure as before, we use Laplace transforms. We use Laplace as a tool to solve differential equations. Take the inverse Laplace, come back to the time domain. This is the eventual answer you get after partial fraction decomposition. I'm going to use this form, but A, B, and C are all the same. Identical to B. identical to C, and I'm going to pull this top panel down. Okay? Alright, so why are we doing all these things? Let's take an example. Okay? So before I take an example, if I look at the system response, so this was x of t, which was f naught by k, 1 minus cosine of omega dt minus psi, tan psi is theta by 1 minus theta square. If I plot this as a function of time, this is what I'll get. I have a certain steady state value of the system. Okay? This is a steady state value of the system. Can anybody tell me what the system steady state value is going to be just by looking at the solution? Yes. Oh, behind you. So he raised his hand first.
F naught over k.
F naught over k.
I was going to say
1. But there is a multiplication of an F naught over k, right? So F naught over k is a steady state value. So we already know that from the theory. So x steady state is F naught over k. So if somebody performs an experiment for a unit step function or for a step input and tells you this is the steady state value and gives you the value of F naught, I immediately know how to find the stiffness of the system. Okay, that's the use of this one. We start from 0 initial condition, so there is a 0 slope to begin with. We rise up and the system oscillates about the steady state value. It never reaches steady state. It reaches it after an infinite number of years, by which time system dynamics will be pretty much moot. Okay, so there is a small band about which the system is oscillating. Okay, this oscillation band keeps reducing over time. 2 points I want to mark here. One, this is the peak of the system. It's going to be called as x suffix p. So x p, peak value of the response. The time at which this peak occurs, I'm going to call it as t suffix p. Okay, so this is t suffix p. So xp is x at t suffix p. So xp is the system response at t is equal to t. There are other things that I'm going to mark on this figure. We are not going to look at them today, but we will look at them on Wednesday. There is something called as a settling time. T suffix s, I'm not going to label, I'm not going to write these definitions today. There is something called as a delay time. The time taken for the system to reach half the steady state value when it begins. So that's called as the delay time. P suffix d. D for delay, P for peak, S for settling, settles down into a nice comfortable mode. And then the time taken to cross the steady state value first before it overshoots and then comes back down is called as the rise time. Okay, that time here is called as 100% TR. We will look at all of these things on Wednesday. I want to focus on 2 things today. suffixes are the following. So P is peak, S is settling, D is delay, R is rise. And the time is all of the times at which these things take place. Okay. So example. Let's say that you perform an experiment. Okay? You perform an experiment, and then from the experimental data, here is the plot you get. You perform experiments. Okay, step input to the system is f naught u of t, and f naught, let's say, has a value of 6 kilonewtons. Hey, this is the magnitude of the step. Here is the plot you obtain. The steady state value of the system, I have these numbers here, is 6 centimeters. Okay? The system response is shown here. Okay? The time taken to reach the peak is given to us. This is T suffix P. So I'm given X steady state is 6 centimeters. P peak is 0.3 seconds. And I'm now going to define a quantity called as the maximum peak overshoot, which is this. This is X peak. This is X steady state. This distance here, the amount by which the system overshoots the steady state value by the largest amount. That's called as the maximum peak overshoot. Okay? So this is maximum peak overshoot. This is given as m suffix p, which is X peak minus X steady state. The value given to us is the following. Okay, I'm going to erase this and write just X steady state here. The percentage maximum peak overshoot, which is written as percentage MP, which is 100 times X peak minus X steady state divided by X steady state. Okay, so this is the percentage of the maximum peak overshoot beyond which the curve has gone. This is given to us as 35%. Given from the data what do we need to do in this problem? We need to find the system second order ODE. Okay, so obtain model it as a second order system. Why can't I model it as a first order system? Yes?
Because it oscillates and versus systems that do that.
But it's a forced response. Yes?
It oscillates when the force response is not an oscillatory function.
Louder, please.
It oscillates when the force function is not an oscillatory function, it's a set function.
Absolutely. So you're close. The right answer is I cannot model it as a first order system because I know, you know, we know that if I have a step input to a first order system, what is it going to show? It is just going to show an exponential behavior. If I have a sinusoidal input to a first order system, it will show oscillatory behavior. But the input here is a step input. So the only system that adheres to this particular command is a second order system. That's why we modeled this as a second order system. Okay? Alright. Good stuff. Let's see what we can do with it. And what's the nice thing about modeling it as a second order system is now, if I have the system ODE, I can study the system to any kind of an input function. It need not be just a step input, it could be a combination of things. Okay? And this is typically how your car suspension systems are modeled. You give it a step input, you look at the oscillatory behavior, you model it as a second order base excitation problem, obtain the system parameters. We're going to do it from Wednesday. And then you see I can now model the suspension to any kind of an input. It could be an impulse. I'm going over a pothole, going up, coming back down. I could be going over a lot of humps, sinusoidal excitation. I could have a combination of many things, you see. Okay? Alright, so start from F0 and X steady state, so we know the solution. So at X steady state is F0 by K. X steady state is given to us as 6 centimeters, so 6 times 10 to the power minus 2 is 6 kilonewtons by K, the stiffness of the system. So the stiffness is 10 to the power 5 Newton per meter. Without breaking a sweat, we have one of the parameters of the system. Okay? How do I get the other two? What are the other two parameters? Mass and damping constant. If I can find the damping ratio, if I can find the natural frequency, I can get the other two parameters. So that's what we're going to do next. Okay? But before that, I'm going to erase this particular panel here, and I'm going to ask you a question. Look at the plot that I have. Can you think of any special occurrences at the peak point? What's happening at the peak point? Anybody? Yes, well, you already answered one question. Let me see if my good friends in the back or this side. I'll come back to you. I'll come back to you. Yes, no, not you. So, yeah, back there.
Derivative is 0.
Fantastic, beautiful. So derivative is 0. Right? I know you all have the same answer, or somewhat the same answer. Okay? So the derivative is 0, which means your good friend calculus is coming to the rescue. Right? So we do the following. So at the peak point, dx by dt is 0. This is one of those painful things that I have to do. Okay? So bear with me. If you want to go and take a sip of water, you're welcome to do that. So I take the derivative of the system response which I have written there. Okay? So this is d by dt of F0 by K times 1, so that's F0 by K, minus F0 by K square root 1 minus zeta square omega nt omega dt minus psi at T peak is equal to 0. Okay, we are getting there, right? F0 by K is a constant, so the first term is not going to be differentiated. The second term, I'm going to employ the product rule and then the chain rule. This is all going to take place in a flash, so please watch out. This is F0 by K zeta square, that's a common factor, I'm going to take it out. Differentiate e to the power minus zeta omega n t. That's minus zeta omega n. Differentiation of that term first. Product rule. Then the differentiation of the cosine term where I have to use the chain rule. Cosine differentiation is negative sign. And differentiation of the terms inside the bracket is omega d times t. So omega d comes out. This is equal to 0 at t peak. I don't have any business with this creature. E to the power minus zeta omega t is a common factor. I can take it out. I can set it equal to 0, but it does not give me anything useful, so I cancel this out. Then I have zeta omega n. The negative sign all becomes positive because I have both negative signs. Zeta omega n is a common factor. I mean, zeta omega n leaves here. Then cosine minus psi plus omega d, which is the following. Which is omega d sine is equal to 0. Omega n is a common factor, get that out. I have sine omega dt minus psi, cosine omega dt minus psi, rearrange the furniture, I get the following. The cosine omega dt minus psi, and I have a zeta, which I have to write here, minus 1 minus zeta square I take the cosine, bring it underneath the sine, so I get a tan. Okay? The tangent of omega dt minus psi with a negative sign is equal to almost there. Now I need your help. What do you call that quantity? Look all around you. Yes?
Psi.
Close. Yes?
Tangent psi.
Tangent psi. Because it's written right up there. Okay? So I have the result that I want. Minus tan omega dt minus psi is equal to tan psi what is the conclusion one can draw from this equation? Yes.
To translate a sine function to a cosine function, you had a WDC minus sine.
I guess, okay, so here maybe I should rephrase my question. For what value of omega d times t will this equation hold true? Yes? 0. That's right, but then I get the time to be equal to 0, right? So this is all a t peak, so I should be putting a suffix p here. Forgive me for that. That's fine there. This is t peak. This is t peak. So 0 is the right answer, that's correct. I'm not discounting that. Can I have another answer besides that? Yes?
2 pi?
2 pi. Somebody between 0 and pi? What's between 0 and pi? 2 pi. What's between 0 and 2 pi? What comes? Pi. Pi comes between 0 and 2 pi. Pi is the right answer because you see this is valid for all omega d times t is equal to n pi. Where n could be 0, 1, 2, 3, 4, 5. Because I have so many peaks, you see. I have an infinite number of peaks. And so it's valid at all the peaks. The slope is 0. I'm looking at the first peak. Okay? So this tells me that omega dt is equal to pi for the first peak. And I'm going to now write my answer. So I have a relationship between omega dt at the peak value, and bring the top panel down and write this result again. So story so far. For maximum peak, the time taken to reach the maximum peak is t suffix p. This is the time taken to reach the first peak, which is the largest peak here, is equal to pi by omega d, or pi by omega n times 1 minus zeta square. Completely useless result because I do not know omega n, I do not know zeta either. But I could make use of this if I knew one of these parameters, and here is what we do. We calculate the value of x at t peak. I'm not going to do this. We can obtain x peak, which is substitute pi by omega d into your solution. And we get the following, okay? Ends up being f naught by k 1 minus I've derived it in my lecture notes. Please take a look at it. I'm not going to derive it here. And so here is what I can do. To calculate MP, which is xp minus x steady state, okay? Or if I want to calculate it as a percentage by multiplied by 100, this is what you end up obtaining, okay? Once again, I'm going to leave the substitutions to my lecture notes. This is the final result that I end up with. X steady state is f naught by k. This is one foundational result that we have. The second foundational result is this guy. And the third result is the following. Percentage MP is 100 times exponent minus pi zeta by. How do you get this? Is by substituting for x peak and x steady state into your equation here. So substitute here. Substitute here. The factor of f naught by k cancels off because it's a common factor for all of these things. And so this is what I end up getting. The third fundamental result, which is in this problem pretty useful because I'm given the percentage overshoot. It's 35. If I know the percentage overshoot, the only unknown in this equation is zeta, okay, which we are going to exercise now. So last step. You're given is 35. So if I just do a brute force substitution in there, I have 35 100 times exponent take natural log on both sides. I'm not going to go through the solution steps. Whenever you see an exponent, what do you do? You take the natural log on both sides. Okay, you can lose the exponential term. So solve for zeta. You end up getting zeta. What should you end up getting zeta as, approximately?
Somewhere less than 1.
Beautiful, something less than 1. Right? If you get it at something more than 1, then essentially something is wrong. This is all garbage. Okay, so I have zeta as 0.32. Once I have zeta, I know the peak time is related to the damped natural frequency. The results that we have boxed, they hold true for any step input to the system in the absence of initial conditions. Okay, they are very generic results. They are not specific to this particular problem. So we are given P peak as 0.3 seconds. This is P peak is pi. Look at the first big box on there. So this is omega n times 1 minus zeta square. Solve. Omega n, you get it in radians per second. Okay? These are the numerical answers. Once I have omega n, omega n squared is k by m, so the mass is k by omega n squared. K is 10 to the power 5, omega n is 107. Put a box and then forget it. So the mass becomes after doing the calculation, so this is 980 kilograms. It's a massive body. Okay? No joke here. And then I can get C. Or I can derive C from defining zeta first. So zeta is C by 2m omega n. This is the fundamental definition that we had used to replace the C by m quantity. So C is 2 zeta omega n. And this is also a fairly large value. 6,170. So this is on the scale of a